Okay. So today we're just going to take a concept that we all know about in life, right? And we're going to look at this in context of forces. Okay, so yesterday we looked at forces that were acting in a horizontal direction. Okay, and from a little bit of logic, you can kind of work out that when we're talking about forces in a horizontal direction, usually there's some kind of pushing or pulling force causing an object to move in a horizontal direction. In one dimension, I'm talking now, okay? So either the car must have something to push it forward, there must be air resistance coming from the front, whatever, okay? Now, the force we're looking at today is the force due to gravity, right? And the weight of an object, right? And on Earth, that force is present at all times, okay? So whenever we're working with objects in one dimension, right? And we're looking them in a vertical perspective, we always have a force working on the object, right? And that force is gravity. So when we're talking about forces and gravity, right, we all learned many years ago in physics that there is this magical number, right, that gravity attracts objects, right? There's a fixed acceleration speed. And sometimes you'll see this notated as g meters per second. And this g is just holding the place of the value of that acceleration. Now, depending on what application you're doing and what stream of science you're in, this constant might have a different value, right? So what's the value that you guys use in physics?
9.81.
9.81 meters per second squared, right? Now, in mathematics, right, we're not really interested very much on technical accuracy, right? We're more interested in application, right? So the theoretical understanding of these calculations. And so to make life easier, we will just use 10 meters per second, just like you did when you were probably back in IGCC. I don't know. Okay? But obviously using 10 meters per second just makes some of the calculations easy. So if we want to consider this force of gravity, force is equal to the mass times acceleration, right? And in our case, well, we are talking about gravity, right? So the acceleration is at a constant speed. Now, this is obviously if no other forces are acting on the object. Okay? So if there was no air resistance, etc. Right, and this obviously gives rise to one of the most fundamental things in physics is the weight of an object. So if we want to think about the force exerted on you by the center of the earth, right? What is this force due to gravity? Well, we can say that the weight of an object, right, the force exerted by gravity, is just equal to the mass of the object times gravitation. We could get the force due to gravity on an object. Right, and this is where working with the number 10 really does make life so much easier for us from a mathematical point of view. Right, on page 43, you can obviously go and have a look there. There's a nice little paragraph on the modeling assumptions. Right, it goes into a little bit of detail onto why we don't really care much for this 9.8 and 10 meters per second. Why, I mean, it's quite a massive thing if we're talking about big objects, right? But because the gravitational constant is not actually the same everywhere, we're not really going to look at it from an accuracy point of view. But if you really want it to be accurate, you'd actually have to know the gravitational constant at the position that you're trying to measure something. Okay. So for instance, the gravity at the poles is weaker than the gravity at the equator, and so the gravitational constant would be different. And so to make our lives easier, we'll just use the number 10. Right, I'm going to grab our first little example. Now, this is just forces again, so I want to remind you that when we're dealing with forces, we're going to draw pictures, okay? And sometimes we're going to draw more than one picture, right, depending on the problem we are talking about. Okay, let's have a look at part A. It says a ball has a mass of 0.2 kilograms. It's thrown vertically upwards out of a window that is 4 meters above the ground. Right, so you stuck your hand out the window on the second floor and you threw the ball up into the air. Right, the ball is released with a speed of 8 meters per second. And very important, they're saying here, assuming there is no air resistance, find out how long it takes to hit the ground. So the first thing we need to do is we need to draw ourselves a little diagram, right? So you can, like I said, the shape of your diagram doesn't make any difference, right? Oopsie, I don't want to, let's go black. So I'll just use a circle. I'm going to be lazy and just copy this guy. Right, obviously all our diagrams, we have to specify the direction that we meet or measuring acceleration in. We need to know the force of the object in this case. So in this case, the only force acting on the object is gravity itself. So it's a downward pulling force. Right, and Kiana, what is this downward pulling force going to be?
9.81 times 0.2.
Sorry, just say that again.
Force equals mass times the direction, acceleration's 9.81 in direction. So 9.81 times 0.2.
Okay, so I want to remind you that this is going to get confusing, and I know this is going to suck for you guys. But when we are going to be looking at examples for mechanics, you are going to use 10 meters per second for the gravitational constant, and not 9.
Okay, yeah. So then it's just 2 newtons. Sorry.
There we go, 2 newtons. Okay. So in the textbook, you'll see they sometimes like to write this like this, right? They write it as 0.2 times the gravitational constant, newtons. So you can either leave it like that and calculate that later on, right? Or you can do it immediately. We know the gravitational constant in our context is 10 meters per second. And so we would have 2 newtons. So this ball has a downward force already from gravity of 2 newtons. Right, the next thing we're going to do is we're going to write down the other bits of information that we know, right? Do we know the acceleration, Zara, in this case?
It will be negative 10.
That will be negative 10, right? Because my arrow is pointing in the opposite direction that acceleration is going to occur, okay? So my acceleration is minus 10 meters per second squared. Right? I also have the starting velocity of 8 meters per second. Right? This is where direction makes an important, right? We're throwing the ball up and we're considering up to be the positive direction. But we could have flipped all of this around. We could have changed that acceleration arrow to the opposite direction. I'm actually going to label that as minus 2 newtons. Right? It's acting in the opposite direction of. And well, the other one we have is displacement. Right? So the displacement in this example is, what is my displacement going to be, Dominic? I'm going to draw a little picture off on the side here. Here's ground zero. Okay. Here's the ground. Right, my starting position, the position that I'm throwing the ball at, is position 0. How far in displacement is ground 0 if this is the positive direction? Right, we're not interested in how high the ball goes at the moment. Right, we're just interested in how long it takes to hit the ground. So do you want to help out there? What's my ending displacement going to be?
Mr. James, I've been lagging out the whole time. I didn't hear anything you said.
Okay. Dominic, what's my displacement, my ending displacement going to be when the ball hits the ground, if I consider my position to be the starting position?
It'll be negative.
It's going to be negative because, you know, the ball's going to go lower. This window is 4 meters above the ground. And so if it hits the ground, it's going to have traveled minus 4 meters in displacement. So your ending displacement is minus 4 meters. Yeah, makes sense?
Mm-hmm.
Okay, now based on the information that we have, we want to work out time, right? So the best formula for this is going to be, I have displacement, I have initial velocity, I want to work out time plus a half AT squared because I have acceleration as well. And now it's just a matter of plugging in numbers and solving for t. So my displacement was minus 4. My initial was 8. My acceleration is minus 10 t squared. Right, if I reshuffle this, I'm going to get 5t squared minus 8t minus 4 equal to 0. And now we just have a quadratic to solve. Okay. I know 5 is a prime number, so I know I'm going to get 5t and t. And factors of 4 are 1 and 4 and 2 and 2. And I need to make 8, so I can see that's just going to be 10 minus 2, or plus 2, sorry. Right? That's going to give me a time of minus 2 over 5 and a time of 2. So which answer is correct, Raya? Time of minus 2.2 over 5 or time of 2?
Wouldn't it be minus?
Yeah,
Wait.
Are we talking about
No,
time? We don't
Yes.
care about the time in the past. We want the time in minus time is time that happened before. Okay?
Yeah.
We
Sure.
know that time is usually greater than 0. So we will select time equal to 2 seconds. So 2 seconds after we throw the ball out the window, it will hit the ground. It'll go up, it'll come down. Everybody happy with that so far?
Yeah.
Okay, right. Now let's look at question B. All right. Question B is a little bit more realistic. Now it says there's actually constant air resistance. Right now, this is against the direction of motion. It's against the direction of motion, right? That means that on the way up, the air resistance is coming from above, and on the way down, the air resistance is coming from below, right? So there's resistance in opposite directions on the journey up and on the journey down. This means that we cannot solve the problem in one step like we just did for the first part, right? The reason we could just solve the question in part A in one go is because the force never changed, right? The force was constant. There was only one force acting on the object, and obviously this caused the acceleration to be the same. So let's have a look at part B now. We have this constant air resistance of 0.1 newtons acting against the direction of motion. So I'm going to need a new diagram, and I'm going to steal this one, and I'm going to steal this one here. Zara, is my acceleration going to be 10 meters per second again?
Yeah.
Okay, no, it's not. Okay, this is where you get caught out. So I'm going to show you why, right? Let's go back to the first example and let's see why the acceleration was 10 meters per second. Okay, I want to remind you that acceleration, right, or force is equal to mass times acceleration. The force in my example was minus 2 newtons, right? We calculated that from the weight of the object, right? Because an object has weight, it has force, right? Its mass was 0.2 kilograms, and we want to solve for A. And so you can see that A would be equal to minus 10 meters per second squared. Right, except this time we don't have one force acting on the object. We have two forces this time. We have the force due to gravity, just like we did before, right? Now, when I throw the ball up, right, I'm going to exaggerate this for a second, right? I'm going to put the arrow there for a second because I want you to think when I throw the ball up, right? Think about driving in a car. The wind comes from the front. So when you throw the ball up, there's a force coming from above, pushing the ball and slowing it down, okay? Now, obviously, in the convention is not to put this at the top here, right? We're going to put this force at the bottom. So now we have two forces acting on this object on the way up, right? We still have this 2 newtons. This is the force due to gravity, right? And this time we also have this other force of air resistance, slowing and pushing the ball on the way up, right? So I need to recalculate my acceleration. The acceleration is not going to be 10 meters per second this time because I need to also account for the fact that I have air resistance, okay? This is why, guys, if you're wondering, a skydiver gets terminal velocity because as the resistance, the air resistance increases, right, it causes the acceleration to decrease, and eventually you get constant velocity. If there was no air resistance, the skydiver would continue accelerating for infinity. Okay, we need to take force is equal to mass times acceleration, right? And we need to remember that this is net force, okay? So my net force is just the sum of all the forces acting on the object. So this is going to be minus 2 newtons minus 0.1 newtons. The weight of the object is still 0.2 kilograms, and the acceleration is what we're trying to work out. So you can actually see we're not going to get 10, right? This is going to become minus 2.1 newtons. And if you divide 2.1 by 0.2, you're actually going to get an acceleration of minus 10.5 meters per second squared. Okay. So the only time the acceleration will be the same as the gravitational constant is if there are no other forces except for gravity acting on the object. That kind of makes sense, right? So if you have more than one force acting on an object, you must remember to recalculate the acceleration. Now, the acceleration, if you think about it, is going to be different on the way down because the air resistance is going to be coming from a different direction on the way down. Okay? It's actually going to be coming from above. This is why we have to do this problem in 2 stages, right? Because the force is different in both directions. Okay, other information we can use, right? We know the initial velocity is equal to 8 meters per second. Kiana, do I know my displacement? No, right? And I might need that later on. Okay, so we don't know the displacement. Zara, what's my final velocity going to be at the end of the upward motion of the ball?
Wouldn't it be 0?
It's going to be 0. So when the ball gets to its highest point, it will have no velocity. Okay? Time is what I'm trying to work out. I know the acceleration is minus 10 meters per second. So I'm going to need to work out the time that this takes, right? So the easiest equation to find time with the variables I have is v is equal to u plus at. Our velocity is 0, our initial velocity is 8, and our acceleration is minus 10.5. I'm being very lazy here. This was not 10.5. And time is what we're trying to solve. So I'm going to get 10 divided by, or 8 divided by 10.5, right? So I'm just going to start my calculator up because obviously I've done this problem before and I know that I'm going to get some nasty number, okay? Now that's the time. If you push the decimal button on your calculator, you're going to get a number that looks like this, 0.761904, etc. Right? Now we are talking about time, and you might not think that this makes much of a difference, but depending on the type of problem you were solving, accuracy would become a very important thing, right? So my suggestion is save this number in your calculator or leave it as a fraction if you have got a fraction right until the end, okay? And we'll change it at the end of the calculation. Right. So I want to look at the journey that my ball has now traveled. So I'm going to draw myself a little picture here quickly. Oopsie, sorry. It's not liking me today. Okay, this is what I'm going to call ground 0. That's where I threw the ball. I threw it up. This took about 0.76 of a second, right? What I need to know now, right, because I don't know the speed that the ball is going to reach on the way down. I don't know what its final velocity is going to be, right? And I'm not interested in the final velocity, right? But I'll need a bit more information in order to calculate the time, right? I will need to know the distance that this object is going to travel. I know the bottom half is going to be 4 meters because I'm 4 meters above the ground. And I just need to work out this little extra piece over here. Okay? So when I threw the ball out the window, it went up, it got to a certain height, and then it started going down. So if I can work out this small bit of displacement here, I can work out how far the ball is going to travel on the way down. Okay? So the formula we will choose to use here, right? Because we don't want to rely on the fact that our time is accurate, right? We always assume that maybe we've made some mistake. So we rather rely on an equation that doesn't use the previous answer. Okay? So I can do that by using this formula here, right? It doesn't rely on me knowing the time to calculate the displacement. Right, my final velocity is 0, my initial velocity is 8 squared. My acceleration is minus 10.5, and displacement is what I'm trying to work out. So again, when we put this in the calculator, we're going to end up taking 64 and dividing it by 21. And again, for reasons of accuracy, right, we can write this as a fraction for now, right, because it's more accurate, right? If you convert this again, it becomes a number that has 0.47619, right? If you round too early, right, you can get very big inaccuracies in your answer. So I'm going to leave my displacement as a fraction for now, right? In my final answer, I will round appropriately. In the textbook, they've rounded to 3 significant figures already. I highly discourage you from doing that. Especially when you see how close the answer is going to be, you'll see why it's important. Right, this was the journey up. Now we need to consider the journey down. So I'm going to be lazy and I'm going to steal all of this stuff. And we're going to look at the next half of the journey. Right, so I like the way that they've done this in the textbook because I like the idea, right, that they are showing here. Right, let's first of all think about the forces acting on this object, right? We still have this 2 newtons from gravity, right? That hasn't gone anywhere. Gravity doesn't just disappear because the ball changed direction. Except this time the air resistance is not coming from above, all right? The object's now falling towards the ground, and so this force is actually acting in the opposite direction. So if I had to put it underneath for you, imagine that this arrow here is indicating the wind, right? As you're falling down towards the ground, the wind is coming from below, and there's a force from that direction. Okay? So let's put it into our diagram here. I think I'm just going to move everything down over there. Right, they said that the air resistance is constant, right? So the force is going to be 0.1 newtons again in this direction. Now, because I've separated these two scenarios completely, I'm isolating them. I can actually choose in which direction I want to consider my acceleration. Okay, so on the way up, I considered the positive direction to be upwards, right? And on the downwards direction, I'm going to do exactly the same thing, right? I'm going to flip the direction that I choose to be positive, right? So acceleration is acting now in that direction, okay, towards the ground. This means that my weight, the force from gravity, is now a positive 2 newtons because it's acting in the direction of acceleration. And my air resistance is acting in the opposite direction, and so it is negative, right? You don't have to do this. You can keep your acceleration and everything in the same direction. You'll get exactly the same answer, right? I'm just showing you that you You can always change your perception of the direction you choose to be positive, and you'll still get the same outcome. Okay? The important thing is to look at the direction of these. Okay? Right, we need acceleration, so we need to work it out. We have the forces, so we need to find the net force. So again, force is equal to mass times acceleration, remembering that this is the net force, okay? So the sum of all the forces, right? I chose to choose acceleration in the direction of the ball again, and so my force downwards is now positive, and my air resistance is negative. The mass of the object is still the same, and we want to work out the acceleration. This is going to give me 1.9 newtons equal to 0.2a. If I divide by 0.2, I'm going to get an acceleration of 9.5 meters per second. So you can see there's a massive difference between my acceleration on the way up and my acceleration on the way down. Okay. Right, my acceleration is positive. It's in the direction of motion, so it's 9.5 meters per second square. My initial velocity is 0 because the ball at its height is going to be not traveling at all. I'm not interested in the final velocity, right? I do know that the displacement of this object is going to be, what's it going to be, Toya? How far is the ball going to fall before it hits the ground? Well, have a look over here. It's going to travel that 4 meters from the window to the ground, and it's going to travel this distance that we just worked out, right? And that distance is this 3 point something something something.
7.5.
Well, 7.05, okay?
Oh, okay. 7 volts.
So what do we have here? We're going to have 64 over 21 plus 4. $148 over 21. Right, we want to work out time. So we're going to choose an equation that can give that to us in one go. And the one that works the best is displacement equals initial velocity times time plus half acceleration and time squared. And from here, we can just put in all the numbers. Okay. Because I selected to change my direction of motion, this displacement that the object is going in the direction of motion, and so it is a positive 148 over 21. Our initial velocity is 0, so that causes that to become 0, right? And here we have a half. My acceleration is 9.5 t squared. I'm not going to bore you with the calculation, right? We're going to get a time of 1.22 seconds. Right, that's already been rounded to 3 significant figures. Right, is that my total time, Keanu?
Yeah.
No, that's just the time for the second phase, all right? I need to remember that there was time from the first phase as well. That was that 16 over 21. And so I'm going to add the time 2 of 16 over 21. So 1.22 plus 16 over 21. And I'm going to get a time of 1.98 seconds, rounded to 3 significant figures. So there's a 0.02% or second difference between having that little bit of air resistance and